I'll give it a minute or two. No, we do have, I have no idea how long these things are going to take. So hopefully this one's, it's probably a little longer than the last one, but a lot of it is paid. Okay, well let me, I've turned on the video already, so I'll get started here. What was I saying? So there's no telling how long these things are going to take. My thoughts are this one will probably take a little longer than the last one, but a lot of the material is kind of more show and tell than actually gathering a bunch of data. And in Gupta's schedule, he said this was going to be the quote fiber lab. Well, we're kind of mixing it up a little bit. The first two parts of the experiment, there's going to be 4 parts. The first 2 are more objects related and lasers back again. We're still looking at the properties of lasers and polarizations and retarders. So part 1 is going to be looking at polarizers. Part 2 will be putting a retarder in the picture and seeing how that affects. And we got some data on those 2, just the same as you did before. Point. 8 samples, guys. How was that all done? But when we're gathering data, it's really hard to fit a curve with it on the 8 samples, right? I think somebody at one time I was maybe dozing off or something in the back, and somebody said, is 10 enough? And I'm like, yeah, 10 is probably enough, but 8, no, 8's not. I mean, if you have a small number of points, the curve always fits, right? So it's not the point. Right. So maybe, I don't know, 10, 15 points, something like that is kind of the minimum. I don't know if you're familiar with the T sample statistical tables for T. That's not really based on a minimum sample size of a net. There was actually some Irish guy figured that out working for Guinness, and he was doing statistical analysis back in the turn of the century on quality control in Guinness. You wouldn't think it would be a very scientific endeavor, but it is. Okay, so what else? First one is polarizer, second one is pathway retarder. Then we're going to look at some anisotropic crystals. I've got a piece of calcite there, and we'll take a quick look at that. That's more of a show and tell. There's really draw a picture, write a paragraph or paragraph. Then part 3 and 4 will be a little bit more involved. We're going to hook up some fiber optic cable and hopefully be able to observe the modes in a multi-mode fiber. And should be all half for you. Observe the modes in a multi-mode fiber, and if we can get a chance and get it to work, I've also got a piece of single-mode fiber. But I don't have a very good coupling mechanism, so it's going to be hit and miss. It'll be more like, I'll tell you what you're supposed to see, everybody's going to nod and say they've seen it, yeah. And we'll move on with that. Part 4, we'll measure the optical power through a bunch of components. We'll first measure the power coming out of the laser, that'll kind of be our 100% number. Then we'll stick a piece of fiber in there, we say, oh, okay, well, no, maybe not, but okay. Then we'll stick another piece of fiber in there, and we can do the power calculations as part of the lab for what your dB loss is at each point, right? Sound reasonable? Let me get you guys started with the first experiment. I'll point a different scribe this time. Who wants to be scribe this time?
I can do it.
You want to be scribe?
Sure.
Says the guy that didn't bring his lab with him.
Hold on. I brought an electronic.
I'm scared. You guys should be scared. You're going to do it online? Okay.
Electronic copy. It's even better.
I know. I was reading
a spreadsheet up and everything.
All right. I was reading a cartoon over in North Europe where it was a Dilbert about, some guy making fun of the old guy who was using his desktop computer. And then Dilbert responds, no, I've also got a laptop. And the smart guy says, yes, I'll text the 90s and let them know. Cruel. Okay, so part of little show and tell at the beginning. I'm going to talk for a few moments before we jump into the first experiment. Talk a little bit about. I've got some polarizers here that we can play with. I don't know if you guys played much with this stuff. they're kind of, when you take two polarized pieces of polarized, put them in front of each other, twist them 90 degrees. See that? It's kind of a nice little experience. You know, we think of light as being this electromagnetic wave that's very esoteric, and there's nothing that we can put our hands on that can demonstrate that. But you just demonstrated it with two pieces of plastic there. So, oh my God, there is an electric field there, and it actually interacts, right? You know how to make that plastic is just long strings of polymers. And you can think of it as being a grating, right? And if it's a grating, the waves that are going up and down can't get through the grating, but the ones going across can.
What type of spacing are we talking about between this phone?
It's got to be on
The order of like a quarter?
It's probably shorter than that. It's got to be shorter than that. Because otherwise you get interference.
Isn't that how they do like 3D movies nowadays? Where like one...
Yeah, I was, and you know, I was going to bring a pair of 3D glasses with me, but I don't know how the polarization is working. It's not vertical or horizontally polarized. I think it's circular polarized. Because when I stuck my 3D glasses and used this, I'm like, huh? That wasn't what I was expecting. So I said, I'm not going to bring that up in the lab. So thank you for bringing that up in the lab. I think they're circularly polarized, but I'm not sure. It's almost the only thing left that it could be.
Yeah.
And my guess is one side is right circular and the other is left. That'd be my guess how it works. The other way to do it is with blue and green, but that's pretty clunky.
Yeah, this is not good than that.
It still works pretty good. What else go on? You go into a store and you're going to buy a pair of polarized glasses, and you're trying to look, are they really polarized? You know, maybe they're from some Absurdistan or something, and you're not so sure about that country, so you say, I don't know. You can take two pairs of glasses like this and do the same trick. Oh, they are polarized, okay. You know. That's my show and tell. If you guys want to look at this, I'll leave that out. Leave that for my experiment. So that's going to be experiment number 3 there, where we start looking at the anisotropic crystal. But let's get started with the first part using the polarizer. Let me just explain the setup. Laser, I've got a polarizer in front of the laser just for emphasis. And it gets us to think that, you know, yeah, it is actually polarized. You could take it out, it seems to work just the same, but this is kind of a double check that your beam is actually polarized. And then you've got an adjustable polarizer path there, power meter. What else can I say?
You take the first one, someone else. So, either power right in.
Catch a whole lot of traffic.
Yeah, they're on.
You just need to adjust this negative 90 to 90, right?
There's a little bit of a weak shot.
Turn that, you want to read it off.
One guy call out an angle, and then the next guy call out the power.
Alright, so you want to start the angle off on the power?
Alright, 0. I'm going negative 90, 90. No.
It's, yeah, well, how is this written? This is written in like 0 to 1.
Now remember, the meter also has a scale. So if you think that's, you might want to see if you'd be better off working on a higher scale.
Is this the scale?
Yeah, that knob. Flip it up on the other direction. Yeah.
There we go.
For this first experiment, use it in that scale. You'll probably have to change it for the next experiment because the halfway plate.
0.
You do it. Let me know when you're there again.
Just making sure it's married. 0.
Alright. 215 point, changing.
What's the same?
It's microwatts. And we're changing tens.
Alright. 10.
221. I'm just not going to give you the point digit because it's.
Okay, so this is part 1 of the experiment.
We've got a power meter connected up to a detector, and we've got a variable polarizer, and we've got a fixed polarizer, just to make sure that our laser is polarized. Now, the last lab we made the assumption that the laser was polarized. Here we're being extra careful because we're going to essentially do the experiment where we vary the polarization of the light here by adjusting this optical element from 0, 10, 20, 30, 40, 50, and as we vary that, we can see that the power is going down. So now that's at 0, 10, 20, 30, 40, 50, 60, 70, 80, 90 is the, we expect to be at the minimum, and then we keep going 100, 110, 120, see it's coming back up, 130, 140, 150, 160, that's 180, and we're back. So 180 is exactly off. We're right back up where we started from. So the light varies from, that's 100 and 187, 190 microwatts to a minimum at around 9 degrees of 18, 19, and then back all the way up again to 180, 190. There we are, it's 188, 190. Okay, so that's the first part of the experiment. So with the second part of the experiment, I've replaced the polarizer with a half-wave retarder. Looks very similar. Both is for adjustable scales, so you can adjust the angle. So the retarder's in place. You can see the light shining on the photodetector here, laser here, and we're going to look at some readings. So let's starting at 0. I've got 0.55 milliwatts, 10, 0.55, 20, 0.548, 30, 0.53, 40, 0.53, okay, so starting at 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So the point of this experiment too is that you can see a slight change as you adjust the retarder, but the bottom line is that the retarder essentially just changes the polarization of the light without reducing the output. So, brief interlude here. I didn't take video when I was up at UVA of part 3 of the lab where we did the experiment on the anisotropic crystals. So I'm going to give a quick demo here. I don't have all the equipment here, but I'll give you an idea, so you should be able to do a decent lab report. I did some pretty good drawings of this on the paper I handed out that I emailed everybody. So the first part essentially is you take a piece of paper with a black dot and you essentially look at the black dot through a piece of an isotropic crystal, and you look really close and you should see, instead of a single black dot, you'll see a blurred image with 2 black dots, depending upon how close you put it up to your eye. And then the second part of the experiment, you take a polarizer. I've just got a thin piece of polarizing film here mounted in a 35mm slide. You then take that slide, you look through the combination, and you rotate the slide 90 degrees and back. And as you rotate the slide, you should see the second dot disappear and the first dot reappear. I think all I asked in this experiment was to just write a short experiment, just a short paragraph describing it. And it shouldn't take too long. Okay. Okay, so this is the third part of the lab where this is part 1 of the fourth part, where we're looking at the output of the laser being coupled to a section of multimode fiber, and then at the end of this particular multimode fiber there's a little bit of a lens, and we can see the dot that's produced on a piece of paper. And it's kind of hard to see there, but if you look very closely you should be able to see, that there's some dots going on and the output of light, and that's showing you the various modes of light in the fiber. If we were doing this experiment, and I'm not going to do it here for brevity, we did do it in the lab with some of the students. We hooked up a piece of single mode fiber cable that was even more difficult to couple, and we were able to show that was a very smooth circle. Looked very Gaussian in shape, which is what you would have expected from a single mode fiber. Okay. So here now we have our laser now hooked up, and instead of having the multimode fiber, we have a piece of single mode fiber hooked up that the people that were here on site doing the lab will testify was almost impossible to get lined up. And we did hook it up in the lab, and we're able to see a very nice single mode output from the fiber. I'm going to turn the light off now briefly. And now that I've got this hooked up, you can see that I'm not quite seeing single mode here, but we're seeing some very, very nice mode shapes here. This looks like a third mode of reflection. So what that means is that there's actually, for this wavelength, there's enough coupling of the light and the fiber to support 3 modes. That's a very nice shape. And some of the earlier on in the lab we were able to see, I think we were looking at 2 modes. So this is the fourth part of the lab. We're measuring the optical power losses in a system with fiber optics. The first part of that, we've got a power meter hooked up to a photodetector, and we're measuring the output power directly from the laser. There's no other optical components in between. And here we're seeing something in the order of 0.6 milliwatts. with nothing in the path. So that's kind of the first part of that experiment. Measure the output power directly from the laser. So once again, this is the second part, part 4. Now I've got the laser connected to a piece of, couple it with a piece of multi-mode 50/125 fiber, connected to another coupler that's in front of a photodetector, the same photodetector. The detector's reading about 115 microwatts, which is a significant reduction in what we measured earlier. The important part I want to bring out here is that the coupling of the laser into the fiber is incredibly sensitive, and all I have to do is just even make even a slight change, tapping the back of the detector, and now I've jumped up significant in the coupling. If I adjust my little micrometer here to where I've got lining this up, I can cause a huge difference. Okay. Okay, so the last part of this experiment is to hook up a second section of multimode cable. Once again, I was reading 171 microwatts after the single piece. I connected a second piece of fiber optic cable in there, and now I'm measuring 158 microwatts. So there's the numbers that we used for the lab. 171 for a single piece of fiber, and 158 for two pieces of fiber. Once again, the couplings are very, very fragile, and you've got to really line them up very carefully to get this experiment to work correctly. Okay, so I'm going to talk for just a few moments about the last part of the lab, involving the different sections of fiber and calculating the power losses. As everybody could tell, it was very, very difficult to get all of this lined up and get any meaningful results from the experiment. But the first part we really had a lot of difficulty was trying to see the modes of reflection through the single mode fiber. And when I wandered home, I kind of had a little bit of a chance to think a little bit further in that. And the bottom line there is, yes, it's single mode fiber, but that single mode fiber is designed for 1500 nanometers of wavelength. So now we take our 632 nanometer helium neon laser, and there's a lot more room for extra modes of reflection in that. So we end up with multiple modes, still a small number of modes, and I think the image I showed that I sent out with the update I sent had a really, really nice picture of some of the modes there that was very, very similar to what was in the book. I think that was mode 0,2, and it was very similar to what the textbook shows on page 97. So the other part, that was the other part 4, where we calculate the power losses. That also was a little bit, I think I used the word vexing. But special thanks to Tribbed for staying behind and working with me by using a better coupling to get the fiber to get the light into the fiber, and then figuring out the right way to tighten down on the coupler in between the lengths of fiber. We got some better numbers. So we measured the total output of the laser to be 600 microwatts, and then with one length of fiber we got 171 microwatts, and then after hooking up the second section of fiber we got 158 microwatts, and they're the numbers I'd like to see everybody using when you decide to turn in the labs. Okay, hope the lab was useful to everybody. I learned a lot doing it, which is always fun. So good luck, and talk to everybody when we do lab number 3.